Basically, I will just introduce you a little bit.
Okay.
So welcome to APRG seminar. It is my pleasure to introduce today's speaker, Olli Saari from Universitat Politècnica di Catalunya. And he shall be talking on quantitative characterizations of weights and parabolic boundary value problems. Okay, so with this, I would like to invite him to deliver his talk, and I also request all the participants to mute their microphones. So over to you, Olli. Sorry.
Okay, thank you. So thank you once more for the invitation. This talk is about boundary value problems for elliptic and parabolic PDE, and it's based on a joint work with Simon Bortz from University of Alabama and Moritz Egert from Technische Universität Darmstadt from Germany. And this talk has basically two themes. First, there is a result on elliptic boundary value problems, which I will discuss a bit more in detail, because this is a work that has already been posted in arXiv. And then there is the second part about the parabolic boundary value problems, which is about to be posted, hopefully within 2 months. And there I will briefly give some comments on what it is going. But before going to the actual results, I will give quite elementary introduction on the topic, because this is maybe not well known for everyone, or not well remembered by everyone, what these kind of questions are about. So let's start from the results in elliptic partial differential equations, and let's go to the thing which is familiar to all of us from complex analysis. So let's consider a bounded and simply connected domain in the complex plane. And now we are solving the Dirichlet problem in this domain with continuous boundary data. So there is, for instance, the Perron's method that allows us to construct for any continuous function on the boundary a function UF which is continuous up to the boundary and also defined inside the domain, so that this function UF is harmonic and it attains the boundary values in terms of limits. And of course, now we can solve the problem for continuous boundary data. The harmonic functions have some special properties, namely the maximum principle and something more. And using the maximum principle, we can define a functional for each point inside the domain. So we fix Z in omega, and we take the mapping that takes the boundary data, it solves the Dirichlet problem, and it evaluates the solution at the point Z. And this functional is positive bounded linear functional. This follows from the maximum principle, the boundedness, and positivity also. And now we have bounded linear functional on the space of bounded continuous functions on the compact set. So this is represented by a radon measure. And this radon measure is called the harmonic measure with pole at Z. Okay, so now we have this harmonic measure. And of course, it was originally defined for continuous functions, but because it's measure, we can define it on measurable sets. So it is indeed a measure. The properties of measure are related to the linearity of the equation, basically. Okay, and then what about the harmonic measure? The first thing is the intuition. So using the probabilistic interpretation of this problem, we can say that if we start Brownian motion at the point Z, then the probability of first exiting the domain through the set E is exactly the harmonic measure of the set E. And this gives some idea how this measure is distributed. And then one basic property which is important for the rest of the talk is the change of pole property. So if we take 2 points Z and W inside omega, and we define the respective harmonic measures, then whichever set we take, the harmonic measures with poles at Z and W are of comparable size, and the comparability is with respect to a constant that only depends on the pair of points and nothing else. And that's why some measure theoretic properties do not depend so much on the point Z. For instance, if we say that the measure is absolutely continuous, this is a thing which is independent of the point Z. And also properties like being in a Muckenhaupt class are also independent of the point Z. And that's why in what comes, we might be talking about harmonic measure without making reference to the point Z or W, because if the properties we talk about hold for one of them, it typically holds for all of them. Okay, and now let's recall the classical results in the complex plane. So first, we can start connecting the measure theoretic properties with the geometric properties of the domain. So the first property is that if the harmonic measure happens to be just constant multiple of the arc length measure, this forces the domain to be very symmetric. You can imagine the Brownian traveler. If it hits every point with the same probability, or every arc with, or every piece of the boundary with the same probability, there are not so many alternatives. The domain has to be a ball which is centered at the point where the Brownian motion starts. This is maybe not so interesting. A bit more striking is the following one. So if we know that the harmonic measures of the interior and the exterior domain, you can also define the harmonic measure for the exterior domain. It's slightly more technical because you have to take into account you're in an unbounded domain, but you can still do it. So if both these are doubling, this means that the domain is actually a quasi-circle, and this implication can be reversed. It's very striking that it can be reversed. And now, what is a quasi-circle? The simplest to state definition is that the boundary of the domain is image of the unit circle under a global quasi-conformal self-mapping of the plane. And what does this mean in more geometric terms, or sorry, more elementary terms? One should think that the domain cannot have cusps of any type. So it can have corners, but it cannot have cusps, like the graph of modulus square root modulus x would have a cusp around 0. So these kind of things are not okay.
So are you considering this thing in domain R2 or in RNA? These are the things.
This slide is still in the complex plane.
Oh,
so
you are
R2.
still in a complex plane situation, right?
Yeah, for the introduction, we are in the complex plane. This can be generalized further, as we will see.
Okay.
Okay. And in higher dimensions, one wouldn't talk about quasi-circles because that's not so good notion in higher dimensions anymore. Okay, so now we have one measure theoretic property, doubling, and one geometric property, quasi-circle. And these are if and only. Then the next property in terms of weights or measures is the A infinity property, which if you don't remember, it means that you can reverse basically the Jensen's inequality for exponential for all cubes. So you always know that integral average of the weight in any cube is bounded by a constant times exponential of integral average of the logarithm. So this is reversing Jensen's inequality. If this holds in every cube, you say that your weight is in A infinity
what is
class.
phi here? Small phi, omega phi.
Yeah, just a second. For the notation of this statement, phi is the Riemann mapping of the domain. So because omega was simply connected domain, we know that that it is image under a conformal mapping of the unit disk, and this conformal mapping is phi. And then for each r, we can apply this Riemann mapping for a subdisk B0R, so we get the subdomain. And now if all these subdomains have their harmonic measures in A infinity with respect to the arc length measure of the corresponding subdomain, We know that the domain is so-called chord arc domain, and also this thing can be reversed. And now chord arc domain is something slightly better than quasi-circle. To somehow state this idea better, one should use an alternative definition of quasi-circle, namely the three-point condition. So we can also define the quasi-circle as follows. So we take the boundary of the, or we take the quasi-circle, then we take 2 points from there. These 2 points divide the quasi-circle in 2 components. We take the shorter one, and we choose a point from the shorter component. And now we draw a triangle with these 3 points. And we say that the smallest side of the triangle must be bounded by constant times the sum of the longer sides. So we are basically reversing the triangle inequality up to a constant. This is a way to say that there are no cusps. Okay, and now we were using just the Euclidean distance on the points at the quasi-circle. And what happens with chord arc domain is that we state the same definition, but instead of the Euclidean distance, we use the arc length distance. And there is the assumption that the boundary of the domain must be a rectifiable curve. So in that sense, the chord arc domain is rectifiable quasi-circle. And now what are the examples? The quasi-disk, or the domain bounded by quasi-circle, it can be as bad as the von Koch snowflake, whose boundary has dimension greater than 1. But chord arc domain is better because the boundary is rectifiable. And an example of chord arc domain is any bounded Lipschitz domain. But chord arc domain can be worse. For instance, if we have some kind of spiraling in the end, in the domain, so that it cannot be described as epigraph of Lipschitz function, you can still be a chord arc domain. Okay, and now these chord arc domains are very important in the analysis of boundary value problems, because there is an additional theorem which tells you that the LP-Dirichlet problem can be solved if and only if the harmonic measures are in the reverse-Hölder class with exponent p prime. And in particular, we know that the Dirichlet problem for some LP is solvable if and only if the harmonic measure is in A infinity. And now this Dirichlet problem in LP is of course different from the Dirichlet problem with continuous boundary data. So the idea is that we first solve the Dirichlet problem for the continuous boundary data, and then we would like to prove that a certain non-tangential maximal function is bounded in LP, so that we can make sense of boundary values in LP sense. So the non-tangential maximal function is defined by, for each point, we construct a non-tangential approach region. This is slightly technical in more complicated domains, but okay. In principle, close to the boundary, you must be able to find a cone that goes to the boundary. And then for that point, you define the non-tangential maximal function as taking the supremum inside that cone. And if this non-tangential maximal function is in LP, you know that there is convergence almost everywhere for LP functions. So that's why you can say that the problem is solvable. So you first solve it in dense subclass, and then you prove the estimates which allow you to say that convergence happens also in LP. Okay, so this is the historical background. And now let's move on to the actual topic. So after the harmonic functions, the next object to study are the divergence form elliptic PDEs. So instead of div grad U, we study div A grad U. And we again study the same problem, but now we ask what kind of matrix we can put here. And the typical conditions for basic PDE theory are the conditions on boundedness and measurability. So first of all, the entries of the matrix are bounded and measurable. And second, we want that uniformly in the variable x in omega, the matrix has all its eigenvalues bounded from below by some fixed constant capital N. This is the uniform ellipticity. And this is the basic setup for PDEs. But to do boundary value problems, we typically need something more. And these something more assumptions will be commented later in course of the results. And the motivation, one motivation for elliptic equation is that if we want to study the Dirichlet problem even for Laplacian in higher dimensions, in rough domains, then we typically would like to do some kind of coordinate change to reduce the rough domain to good domain. And when we do the coordinate change, the Laplacian is converted into divergence form elliptic operator. And studying Laplacian in rough domains is roughly equivalent to studying divergence form elliptic PDE in smooth domains. Okay, and now let's specify even further. So instead of looking all coordinate changes, let's look at the case where our domain is actually an epigraph. And now the coordinate change we are interested in is flattening the epigraph to the half space. And in this setting, you can of course do the flattening in many ways. The most elementary one is that if we have the epigraph of L-Lipschitz function f, then we just subtract from the last n plus first coordinate the graph function, and then this transformation converts the domain into upper half space. Now, there is slight drawback in this simple approach, namely, the matrix A will not be smooth. It will be just measurable, and this is a technical nuisance, because then we have very limited amount of estimates in the insights, because we would like our solution to PDE look ideally like the solution to the Laplace equation. It should be smooth, there should be all kinds of estimates and so forth. And part of this is lost if we have rough coefficient matrix. And that's why Dalberg, Kenig, Stein, in some order, used the following pullback. So we take first approximation of identity, which is defined with a smooth bump function, integral 1, dilations. And then we define the coordinate mapping by fixing the first n coordinates. And in the last coordinate, we first multiply it with constant, and then we add mollification of the graph function. And now you see that when f is Lipschitz function and we send t to 0, the last coordinate converges to fx. So this at least fixes the boundary to the boundary of upper half space. But now if you choose this constant c very large, you can compute and find out that this rho is bijection from the upper half space to the domain. So it is a good coordinate change. And the pullback of the Laplacian is now divergence form elliptic PDE for some a. And now from the work of Dalberg, he noticed that first of all, the gradient of the matrix is bounded by 1 over t, the last variable. And what's more, if you take t mod grad a squared, this gives you a density of Carleson measure. Okay, and so what do these things mean? So if we fix the terminology so that a set of the form ball of radius r times interval of length r starting from 0 is a Carleson box. And the upper half of the Carleson box is called a Whitney box. So now if we look at this gradient A, which was bounded by 1 over t. So if we take the measure dx dt over t, and we compute that measure of a Whitney box, we will see that it will be the n-dimensional measure of the ball, B. But if we try to compute the measure of the Carleson measure, we have blow up, because 1 over t is not integrable down to 0. Now the condition of this t mod grad A squared being Carleson measure means that that one has measure of B for the whole Carleson box. So this means that if we just applied this third item to the quantity in fourth item, we cannot measure the Carleson boxes. But the fact that this fourth item is slightly better, it's even Carleson measure, means that it behaves as well for the Carleson boxes as for the Whitney boxes. Okay, and now once these 4 properties were found, it was an idea in Dahlberg's work that one should somehow measure the distance and smoothness of the coefficient matrix in terms of this last Carleson condition. And to study the problem in Lipschitz graphs, he was using these things. And then he made the following questions. So he first asked that, suppose I have a coefficient matrix A0, which I assume to be so good that the corresponding elliptic measure is in A infinity. And now if I perturb that measure so that the perturbed matrix A is close to the good matrix in the Carleson measure sense, can I say that this being closed as the Carleson measure difference being finite is enough to make the perturbed matrix have elliptic measure in A infinity? And this question was answered in affirmative by Fefferman, Kenig and Pipher in 91. So the perturbation question was answered. Carleson measure, the difference being finite in Carleson measure sense implies the elliptic measure is in A infinity. The second question was the smoothness question. So he asked that if my matrix is such that inside each Whitney region, I can compute the oscillation, and now this oscillation gives rise to a Carleson measure. So if this is the case, then the elliptic measure should be in A infinity. This was his question, and again it was answered in positive, this time by Kenig and Pipher in 2001. Okay, and this is somehow what I would say not the last year's results. So we know that the matrix being smooth in Carleson measure sense at level of constant being finite, very qualitative, implies elliptic measure in an A infinity, no information about the constant. And now, of course, the next question is that, can I start making finer conclusions from finer information about the Carleson measure norm? For instance, if the Carleson measure norm is small, can I tell that the A infinity constant is small? And this kind of stability results somehow correspond to the fact that you have a Lipschitz graph, which has some corners, slopes, and so forth. And when you ask the Lipschitz constant to be very small, you would like to see that the corresponding harmonic measures are closer to the harmonic measure of a straight line in some sense. Okay, so what is known? Before going forward, let's fix the notation for the oscillation of the matrix. I was using 2 different things in the previous 2 slides, but let's fix now the following one. So we take the mean oscillation in Whitney cube. This is the quantity alpha A2. It could be alpha AP when we replace the L2 norm in the oscillation by LP norm. Okay, and then we define the measure mu A2 by taking this oscillation squared and dividing by t. And this is a density of a measure in upper half plane. And if this density is Carleson measure, like in the previous cases. This is actually weaker condition than any of the previous ones. Then we call a DKP matrix. Okay, so what are the results when we know something more about the Carleson norm? First of all, there is a result of Lindos, Peter, Michel, and Pipher that for any p there exists delta, so that if the Carleson measure is delta small, then we have Dirichlet problem solvable in LP. So given p, we can always find amount of smallness that allows us to solve the Dirichlet problem. This has nothing to do at level of techniques with A infinity weights. It's using so-called p-adaptive square function. Then the next result is a limiting case. So now we don't say anything direct from the size of the Carleson measure, but we say that it must be very, very small, close to the boundary. So we have this kind of vanishing trace inequality, meaning that when we restrict the Carleson measure to a layer which is at a distance s from the boundary, and we compute these norms, we get some numbers for each s. And then when we send s to 0, these Carleson measure norms go to 0, meaning that very close to the boundary, in some weak sense, the measure is 0 measure. And now, when the matrices for the equations are this good, then the logarithm of the Poisson kernel for the corresponding equation is locally of vanishing mean oscillation. And now Poisson kernel is just a word to mean the density of the elliptic measure. Okay, so this is a result of Bortz, Toro, and Zhao from 21. And this was somehow some work, and it used also heavily an earlier work of David Lee and Mai Boroda on Green's functions, and then some theory of weights, which was done by Corey in 98. Okay, and now after this result, the question from the geometric side was that can one extend this kind of vanishing trace condition implies logarithm in VMO to rough geometric setting, for instance, to so-called vanishing chordal domains, which are a subclass of chordal domains, which is in a way made quantitative, and there is an additional condition telling that somehow in very small scales the domain is smooth. And this was somehow the geometer's hope. But to get there, one had to make first this Bortz-Toro-Zhao result more quantitative, in the sense that we don't just say that one limiting condition implies another limiting condition, but we should make this implication stable, in the sense that we would say that if the Carleson measures are delta small, then the BMO norms are epsilon small. And this was our contribution, which is already out. So we proved that if the Carleson measure is delta small, for some delta depending on the dimension and the ellipticity constants, then for the elliptic measure with pole at infinity, we have the logarithm of A infinity constant bounded by the Carleson measure norm square root. Okay, so the point of this delta here is that this kind of inequality would be, of course, better than linear growth for very large values of Carleson measure, and such a thing we don't claim. On the other hand, when the Carleson measure is having norm very small, then the linear growth would be better than square root. That we don't know, and we don't even expect such a thing to be true. So this is a quantitative estimate just for small values close to 0. An elliptic measure with pole at infinity is a limiting object which is constructed by looking at elliptic measures with finite poles and sending the pole point to infinity while making a normalization so that we get a non-trivial limit. This procedure is done in this theory for the purpose of creating something that has properties of elliptic measure, but in addition has the doubling property, because the elliptic measures, they are only locally doubling, but not globally doubling in this setting. And this is a technical problem that one has to tackle in some way. And the strategy coming from the work of Bortz, Toro, and Zhao was that one proves the results for elliptic measure with pole at infinity, and then one argues a bit more to bring the pole back from the infinity. And somehow our result was a result on weights. And then later, this geometric application was done by David Lee and Mayboroda. Okay, so now I would like to walk you through the proof scheme of this result up to our result. I will leave this last David Lee Mayboroda out. And after the proof scheme, I will comment how the forthcoming work on parabolic equations will be different. Okay, so let's start. The beginning of the proof was an estimate for the Green's function. This was coming from David Lee and Mayboroda. And the idea, and this is the one sentence that people not working on the technical side of this theory should somehow internalize, is that when we have the matrix who satisfies the weak DKP condition, this was the mu measure being Carleson measure, then the corresponding Green's function, which is now the solution with right-hand side Dirac mass and the boundary value 0, and Green's function with pole at infinity is, of course, the limiting object constructed by sending the pole point to infinity and normalizing so that we get a non-trivial limit. So when we have this DKP condition, then we can approximate the Green's function very well with affine functions. This somehow makes sense close to the boundary, because the Green's function is somehow diving from positive values to 0, always in a linear fashion when you go close enough to the boundary. It has a curved graph, but when you go close to the boundary, in the limit, the derivative has really a slope. And more technically, what these people stated, they defined the quantity beta, which is now the one at the bottom of the slide. So you compute the mean oscillation in a Carleson box of, sorry, the mean value of the difference of the gradient and then mean value of the normal derivative. So you would like to say that the gradient is first of all close to constant, meaning that we are comparing it to a mean value. But secondly, we would like to say that it points at the vertical direction. So we are somehow asking how much it differs from constant times en plus 1. Okay, so this is the beta quantity. And now this beta quantity should be small, and smallest of beta quantity means the Green function having a gradient as we want. And this smallest was computed in terms of the square function appearing in the first display. And they prove that indeed, for this Green function with pole at infinity, this square function is bounded by the Carleson measure norm. So this was the first item. And this is slightly technical result, but indeed, this was published as a standalone, because they had their motivation for studying this kind of estimates. But now how to go from this technically looking result for the applications to the elliptic boundary value problems. There was an observation of Bortz, and Zhao that this beta energy, the square function of the left-hand side, can actually be very well used to control the A infinity constant. And the way to do this required one to use a variant of A infinity constant, which is slightly less well known. And the A infinity constant these people used, let's see how we get there. So we fix functions psi and phi, which are bump functions, say, at unit scale. And then we can show that there exists a constant depending on the data of the equation, so that for any point, we can control the quantity on the left-hand side of the first display, which now somehow, yeah, the nominator contains some cancellation. So in a way, it measures smoothness, and the denominator is there just to normalize. So this quantity, these people controlled by the beta energy and then the smoothness condition of the DKP matrices. Another point is that when you take the Carleson measure norm of the right-hand side, you will get Carleson measure norm of this quantity A. But what was the observation is that when you take the Carleson measure of the left-hand side, this is a quantity which is controlling the A infinity constant. Okay, so this was appearing already in the work of Fefferman, Kenig and Pipher in '91, that squaring the left-hand side, taking the Carleson measure norm, if that's finite, you are in A infinity. And then there were these results of Corey I mentioned, that you could get the VMO result. But the Corey did not get the epsilon delta result, and this was our contribution. And okay, because it's our contribution, I discuss it slightly more in detail. So when we fix dimension and we fix a constant, which will be the doubling constant, then there exist constants c and epsilon, so that the following holds. If we take a weight function with doubling constant t, and we let u be its heat extension to upper half space, then we define a measure mu with the following formula. We take the gradient of logarithm of the heat extension, we take modulus and we square, and then we normalize it with suitable factor. And then the result on weights is that if the Carleson measure norm of this quantity is smaller than epsilon, then we have the log of A infinity constant bounded by square root of this Carleson measure thing. And this can be also, in a way, reversed. But please note, this is not the comparability result. It just says that whichever control we try to do, we lose square root. So we cannot really say that something is comparable to something. We can just say that any of the quantities is controlled by square root of the other one. Okay, and this result has nothing to do with PDEs. But to go to the elliptic boundary value problems, we see that there are some technical steps. So first of all, we are using heat extension, and we are having the assumption that the weight must be doubling. This is not quite the setting we saw before. So first of all, they were having these bump functions, but in full space, it's an application of Littlewood-Paley decomposition. It's actually very clearly one page in Stein's book. This was noted already by Corey, and I think it's already in the work of Fefferman, Kenig and Pipher, that when you have this Carleson measure condition for heat extension, then having it for the bump functions, it's equivalent. So this is Littlewood-Paley theory in full space. The slightly more important aspect here is that this thing really requires the doubling condition. And this is the reason why people work with elliptic measure with pole at infinity. Okay, and the proof of this result, or actually the applicable part of this result, is very simple. The other part is slightly more complicated, but I will show the proof of the simple part. It's based on a simple lemma. So let's now, for simplicity, assume that W is smooth, and I will show you the computations. So now, if W is a doubling weight, and we compute the heat extension U, we have the following PDE estimate. So if we first discard all the denominators, and we multiply all the R's to the right-hand side so that it becomes a mean value, L2 mean value inside the Whitney box, then this is a standard PDE estimate. Solution is bounded by its mean value. Okay, this one finds, for instance, in the book of Evans. Now, when we are in a Whitney box and we are solving with positive initial data, if we were solving the Laplace equation, we could say that by Harnack's inequality, all the values in the Whitney box are comparable, and we could just multiply in and out this U and derive this lemma from the PDE estimate. For parabolic equations, this is not quite true in general, because the parabolic Harnack inequality requires you to move forward in time. But now we can use the assumption that our weight is actually doubling. And this doubling condition tells us that we can reverse the time in Harnack's inequality for parabolic equations. And once we have doubling, we get this estimate for solutions of the heat equation too. And now this estimate is the tool which we can use to really compute the right dependency. So let's go to the unit scale. And this is the quantity we have to control. This is bounded by the logarithm of, this should be bound, this is giving the logarithm of A infinity constant. So now we add and subtract some terms. So from the logarithm of mean value at scale 1, we compare the logarithm of heat mean value at scale 1, and we take the supremum just to make this quantity smaller. When we take the supremum, we have to pay. So we compare the supremum of heat mean value at scale 1 to mean value of the heat mean value at scale 1. And then the final term is the mean value of heat mean value minus mean value of the original weight. Now, two of these terms are easy to control. So let's look at the third one. Now we can pull the B integral out. We have difference of logarithm. But log W, now in the smooth case, is log U 0.0. So this is the boundary value. So this is difference of the solution at time 1 and time 0. So we can do fundamental theorem of calculus in T. And then we can use that when U solves the heat equation, the logarithm solves the heat equation with right-hand side constant times mod grad U squared. Okay, and now this right-hand side is exactly the quantity we would like to see. And that's why we can keep it. Then we are left with the Laplacian of the logarithm. Now for the Laplacian, we can apply divergence theorem in the x variable to get a boundary integral. And in the boundary integral, we can use the key lemma. And now the point of going to boundary with the divergence theorem was that this is a way to kill one derivative with discount. So we don't want to convert the derivative to 1 over t, which would kill us, but we convert it to lowering the dimension of integration, which is for free. And then at the boundary, we can use pointwise estimate, and the claim for the third term follows by that. The second term is even easier because there we can do just fundamental theorem of calculus in the x variable. This is just laterally at height 1. So there we can get line integrals, and inside the line integral, we just use the key lemma to bound pointwisely the quantity. And then we are left with the last term, which is slightly more complicated, but not much. And here we just add and subtract the supremum. We bound the supremum from below by mean value. Then we do again a similar computation. And now we should smuggle inside this last integral the uxt squared. But outside the integral, the constant we have is ux1. So we have to control still the ratio of uxt and ux1. But this is compared exactly by the same computation as before. So we say that the ratio is exponential of the difference of logarithms, and we can use again the key lemma to bound this by t to minus c square root of Carleson measure. And now, because we can say that the Carleson measure is small compared to the capital C, we get that this quantity is basically c to minus epsilon. And then we can do Cauchy-Schwarz in the middle display. And this really concludes this proof. Okay, and now let's comment a bit on parabolic equations. So the parabolic equations which are important for these pullback considerations are the following ones. So we have the time derivative, but now if we do the pullback for the heat equation, there will be a lower order term, b dot grad u. So in a reasonable theory, this kind of lower order term must appear. So this is what is called a drift term. So if the first two terms describe somehow how ink is diffusing in a liquid, this last term would mean in a way that there is an external flow B, which is pulling the liquid to some direction. You can imagine how this would look like. Okay, and now for the matrix A, we have the same conditions as before. And for the drift, we have the following blow-up condition. So when we go to the boundary, then we blow up like 1 over the vertical variable, but this blow up at level of constant is epsilon small. And the point here is that at boundary, the first order term is as strong as the second order term. But because there is this epsilon, in all the estimates, the second order term is dominating. And for instance, this condition makes sure that this operator still has as much coercivity as without the drift term. Okay, and now we can again put the conditions on the matrix and the drift. This slide is slightly technical, and I think it's maybe not worth spending more time on this slide. Just the W in the first display is the Whitney region in the parabolic setting. So now in time variable, we have the scaling, which is radius squared. We go back and forth. Then the middle factor is the cube at the boundary. It has radius lambda. And then in the vertical direction, we have again the interval, which is, okay, there is a typo in the second item. It should be lambda. And in the third variable, we have this interval, which is bounded away from 0. So this is the difference in geometry. And now the theorem is that when we have this parabolic setting, and we take any point in upper half space, and we take what is called a forward corkscrew point, meaning that we go up by the radius, which we choose, and then we go to future by basically the radius squared. And now suppose we started from a roof of some Carleson box or Whitney box. We will then fix this pole point and work in a sub box of this original Carleson box. This is the picture you should have in mind. We have the smoothness quantity for the coefficients as before, and then the theorem is as before. So if the smoothness quantity is delta small, then the caloric measure for this equation has the following estimate. This is kind of perfect analogy of the elliptic one, except instead of working with things with pole at infinity, we now work with finite pole. And this was the main technical achievement of this parabolic thing. And of course, moving elliptic to parabolic, there are also other things, like we lack the Harnack inequality in its full form, which makes several steps in the proof more complicated. But somehow at general level, things which are easy to understand are, we work with finite pole, and that's why we had to find a way to do this characterization of weights without the doubling property. So this is somehow one achievement. Then the second thing, which is so we couldn't, for instance, use the heat extension as before, but we had to construct things in that proof very much by hand. And then the second thing is that you see in the display at the bottom, on the left-hand side, there are these delta A's, meaning that when we fix the pole and we fix the size at which we are working, we must go to really, really small scales. And this smallness depends on the size at which we work. This kind of result is enough to give you VMO, but it's not as nice looking as the one for pole at infinity. So if we constructed Green's function and caloric measure with pole at infinity, we could derive the corresponding estimate as in elliptic setting also for that one, but we are really not needing it, because for geometry, this will be the estimate that will be more important. And finally, this delta on the left-hand side is actually necessary, because if it were not there, and you took just the coefficient matrix, which is constant, then the right-hand side would be 0, and the left-hand side would give you a infinity constant 1. But weights with a infinity constant 1 are basically constants. And we know that for the constant coefficient equation, the caloric measure with finite pole is not a constant. So such a result would be too good to be true. And that's why there must be this delta appearing when we work with finite pole. When we go to infinite pole, then things are different. And that's all I had to say. So thank you for your attention.
Thanks, Olli, for a nice talk. Is there any question from the audience? Okay, I have some question. Okay, so the thing is, this harmonic measure, you have given a characterization when it is doubling or something like. Okay, so is there any other characterization for this harmonic measure when it will be exponential kind of thing, like?
Sorry, exponential kind of thing, you mean?
It means this measure is really something like e to the power alpha mod x dx or something.
Something like that, very explicit. Yeah, this I don't really know.
Okay, so and another, what are the kind of domains really? Those are really have not doubling. Can you give some example where the measure is not doubling?
When the harmonic measure is not doubling. Yeah, so the quasi-circle condition, as I said, the easy way to fail it is to create a cusp.
Okay.
So if you have this kind of onion type thing, and you take the point at the very tip. So somehow when you think about the Brownian traveler, it's very hard to get in the top, and somehow in the tip this domain would fail the doubling condition.
Okay. So Ushchab, you have
because
some
somehow there is this kind of scaling mismatch that when you go to closer and closer to the tip of the square root cusp, the measure it keeps decreasing too fast.
Okay. So Ushchab, you have some question you can ask then.
Yeah, am I audible?
Yes, yes.
Yeah, I hear you.
I was just asking about that. If you could give some more details on that harmonic on backward time due to the doubling of the initial condition.
Oh, that's actually an easy thing, because you can write the solution for the heat equation using the convolution with the heat kernel, right?
Yes.
And then you can cut the heat kernel in dyadic annuli. So you have some of k goes from 0 to infinity. Then you have the constant coming from the exponential decay, and then you have mean value at each of the annuli, or yeah. Okay, and now in each annulus, you estimate the annulus by the ball, and you apply the doubling condition to shrink the radius of the ball. And then you compare back to the heat kernel. This is the idea.
Okay.
And now somehow, effectively, you have shrinked from the large radius to small radius, but this radius is the time parameter. So you have actually come backward in time.
Okay. Thank you.
Yeah, so this is much from the heat kernel. If you have more general parabolic equation, it's actually interesting how you could do it, or if it even works.
Okay, are there any other questions from the audience?
I mean, just coming to that thing for more general parabolic equations. So do you look at something like the Redon-Nikodym derivatives of the caloric measures and try to estimate that and to get that? I mean, like for me, Poisson kernel in the elliptic case is just the Redon-Nikodym derivative of the harmonic measures. So
yes, exactly. So yes, this is always what we mean by Poisson kernel. Is the Radon-Nikodym derivative of the harmonic or caloric or elliptic measure. Exactly.
Okay.
Okay, are there any questions from the audience? Okay, if there are no more questions, let us unmute and thus thank the speaker for a wonderful talk. Okay.
Okay, thank you.